So let me start with the basics. When I talk about secure communication, this is the basically scenario that I would like you to have in mind. So we have two individuals, well, you call them Alice and Bob. They're usually good guys. You see, I mean, I don't know why they're called Alice and Bob, but it's just a perfect gender balance anyway here. So that they want to communicate secretly. And then there may be a third party involved, an eavesdropper, quite often called Eve, who may want to intercept those messages. So the question we want to address is this. Is it possible for Alice and Bob to design a system where they can at least know that someone is trying to intercept the messages? So you see, the purpose of eavesdropping, and it's very important to realize, is not to prevent Alice and Bob from communicating with each other. So what an eavesdropper wants to do is to fool Alice and Bob, to make them believe that they can communicate with perfect security, that they have privacy, but in fact, it is not the case, so they are fooled. So this is the case we want to avoid. We want to design a system later which allows Alice and Bob to detect any eavesdropping whatsoever, so that they know they cannot be fooled in this case. By the way, if at any point you want to ask questions, I don't mind if you do, actually. It's just... Right, so people try to solve this problem of secure communication since basically the invention of writing. As soon as people started writing, and as soon as people designed alphabet, you had 30 characters, 30 letters in the alphabet, and then you can play with them. And basically, if you want to scramble your messages, there are two ways you can do it. You can permute letters in your message. You can just place the letter A in a different location and letter B in a slightly different location, and so on and so forth. Or you can do the substitution so that you can, for each letter in your message, you can then put some symbol or some character. And those two are the oldest method of encryption. The permutation goes basically to ancient Greece, to about 400 BC, and substitution, allegedly Julius Caesar used substitution cipher for communication with military commander. And of course, you know, people today use both permutations and substitution. So here is how people implemented in ancient Sparta, how they implemented permutation. So about 400 BC, if you want to send a message in ancient Sparta from one military commander to another, the way you would usually do it would be this. So you would have a wooden button of a certain diameter. And then you would take a parchment and you rub this parchment along this wooden button and you write your message lengthwise. And then you unwrap it. It just looks like this. So you see, this way you permute characters. What is T is still T, well, modulo this rotation here, but it's, you know, what you have here is those letters are not where they should be. The placing of the characters is distorted. Anyway, so you give this parchment to a military courier that would take it from one commander to another commander somewhere else, and the guy on the receiving side would have a wooden button of the same diameter as the sender, would take this parchment, wrap it around the button, and the message would reappear. So this is the first mechanical device that we know that implemented permutation of characters for secure communication purposes. Very trivial in a way, but apparently it's been in use for a while. Now, a little bit later, 50 BC in ancient Rome, and Julius Caesar was using substitution cipher to communicate with his commanders in field. So again, the way he did it was actually quite simple. You take the Roman alphabet and you shift the alphabet by 3 characters to the left. You append them here, and then you have a substitution rule. For A, substitute D. For B, substitute E. For C, F. This is known as the shift cipher, very simple substitution cipher. And then your message that we have just follows this rule. For A, we substitute D. For T, we substitute W. For TW again. For AD again, and so on and so forth. So here we have a very simple substitution ciphers. Now, those shift ciphers where the substitution is generated by shifting the whole alphabet by a few characters to the left or to the right are actually very easy to break. But in general, if you do not follow necessarily if you consider any substitution whatsoever, then there are zillions of those substitutions, about 10 to 26 or so. So one may think that in general it might be difficult to break such ciphers, but that is not the case. In fact, the person who came up with a systematic way of breaking those simple substitution ciphers, and we call them monoalphabetic ciphers because it's just one-to-one substitution. For each letter in the alphabet, we just always substitute the same character. So those kind of ciphers are actually quite easy to break. So the way you do it is just you rely on the fact that in any natural language, the frequency of characters is not uniform, right? So in English, for example, and in fact in most Indo-European languages, the frequency of characters is such that the letter E is the most common one in English. So if you take a typical text, typical English text, and count the number of occurrences of different letters, then you'll realize that the letter E is the most frequent one, followed by T and A. And some combination of letters is also more frequent, like TH appears quite frequently and so on and so forth. So what you can do is just take any cryptogram that was generated by this simple one-to-one substitution and just do the statistical analysis on your cryptogram. So look for the most frequent character in the cryptogram and make a reasonable guess that it's the letter E. And then the second most frequent, then it's probably letter T or letter A. And by doing this very quickly, you actually fill the gaps and you can read this kind of cryptogram. So it's very easy. And the person who came up with this was the Al-Kindi, who worked in what is today Baghdad in the 9th century, who was a polymath, quite a remarkable person in many ways. Okay, so what's next? I mean, if monoalphabetic ciphers are easily breakable and we can break them easily, what is the next best? Well, the next best is what is called polyalphabetic ciphers. The idea is to make not one-to-one substitution, but one-to-many substitutions. And who exactly came up with this idea? Historians are still debating, but most likely it was this chap here, Leone Battista Alberti. So those of you who have interest in the history of art probably recognize him as a famous Renaissance architect, one of those Renaissance men. Among many things that he did, he designed something that is known as an encryption disk, which is sort of like two concentric disks with the letters of the alphabet on the edge here, on the perimeter. And for a given rotation of those two disks, the relative rotation will specify the substitution, right? So you can say, okay, if those are the messages, the letters from my message, then for K substitute P. So obviously you can just come up with a substitution rule between the inner and the outer disk here. And so Alberti had this idea, having this mechanical device, he was saying, why use one substitution? Maybe depending on which letter, on the position of the letter that I'm encrypting, I can use different substitutions. So for example, for the first letter, I can use maybe the shift by 7 characters in this disk. And then for the second letter, I shift by 14, for the third letter by 19, and then I repeat it. For the fourth letter, the shift will be again 7, for the fifth, 14, and so on and so forth. So the first letter is encrypted by one substitution rule, the second letter by another substitution rule, the third letter by yet another substitution rule. But for the fourth letter, you go to the first substitution rule that you use for the first letter, and you repeat it in the cycle. So that was the first idea of polyalphabetic ciphers. And the interesting thing is that, for example, the letter L now is mapped depending on the location. In here, it can be mapped into E, but it can also be mapped into S because, in this case, for this particular example here, in the first location, we use substitution rule shift by 7. Here is shift by 14. Here is shift by 19, but this one is encrypted with the rule number 1, shift by 7. So obviously, this is a different kind of substitution. And that it makes the statistical analysis much more difficult, because in this case it's not really one-to-one. Letter L can sometimes appear as E and sometimes as S and sometimes as a different character. And it took people a while to come with a systematic way of breaking polyalphabetic ciphers. Again, historians dispute. What else do you expect from historians? They like disputing. And then the most likely, the first one who really had an idea how to break it was Charles Babbage, and he did it roughly in the sort of early 19th century. And look, the 15th century till 19th century. So those ciphers were considered as secure ciphers for a long time. And even if those substitutions, if you use many substitutions, they still be considered pretty tough to break by any rules whatsoever. The other thing that makes Alberti's idea of this concentric disk very important is that it was a precursor of many mechanical devices that appeared later on in the 20th century, electromechanical devices, in particular the Enigma machine that was designed by the Dutch guy Schrebius, was basically taking this idea in a way to higher levels. So you would just use several concentric disks, you would call them rotors, and they would just generate a number of substitutions which would form a very complicated pattern. So, so those, the Enigma implemented extremely complicated polyalphabetic cipher that was considered to be like the state of the art at the time. But again, it turned out that a little bit of a knowledge of group theory led Polish mathematicians into breaking this code. So it's so in fact, one should, as we are, this is a Polish aspect of my talk, so to speak, and I always like to give the credit to those Polish heroes in cryptology, so that people should know it's not only Alan Turing who contributed to breaking Enigma, but in fact, the most remarkable team here, led by Marian Rejewski and including Jerzy Różycki and Henryk Zygalski, who were from the University of Poznań, and the two guys who somehow didn't maybe participate directly in the whole thing, but this person, Maksymilian Ciężki and Guido Lange. Guido Lange was the head of the Polish Bureau of Ciphers at the time. And Ciężki was the head of what was called BS4 section, so that was a German section in this. And he was very clever because not only he had this idea to employ mathematicians, mind you, in the 30s, if you deal with cryptography, you employ linguists, people that, who are good at solving puzzles, but mathematicians, who trusts mathematicians? He didn't trust them either. In fact, but he was very clever, he had, Poles had intelligence from agents in the field that provided Ciężki with some transcript of some messages that were also decrypted independently by those three guys. So he could actually compare the messages from two different sources. He never told those mathematicians that he has another source where he knows actually what the Germans are talking about. And comparing the two, he was absolutely surprised that, those guys, those mathematicians, know what they are talking about. They really are breaking those ciphers. So, after, as you probably know, the story of Enigma is known by now. It's kind of a sad thing that most of those guys ended up either in the UK or in Poland in sort of not really recognized that much for their effort. Until recently, I think there's a more and more clear understanding that their contributions were absolutely groundbreaking and they were first-class cryptologists, and the Polish contribution should be remembered. Actually, the Brits probably would never actually develop anything at Bletchley Park without those contributions. Okay, so I gave you a very sort of a brief overview of history of cryptography. If there's any lesson from those slides, that you can see right away that whenever there was a clever way of encrypting something, there was equally clever way of breaking it. And the question is, so if going from Skittily to polyalphabetic ciphers to Enigma and to many other devices that were broken. So the question is, in this in this cycle of this battle of code makers and code breakers, is there anything that can give the edge to one of them? So is there anything that would make code breakers victorious in this particular case? So the question is there a perfect cipher that cannot be broken at all? Can we prove that there is such a thing? And the answer is yes, but and so this partial yes come from this construction here that is known as one-time path. So this cipher is very easy to explain how it works. It's just you write your message as a sequence of zeros and ones. This is not considered encryption. You just use some publicly known binary alphabet. Could be ASCII or whatever you want to use. And of course, this binary text, plain text, has a frequency of a natural language. So if you do statistical analysis, you can easily figure out what is actually written here. Now, we assume that Alice and Bob have a random binary string. So a string of bits that is as long as the message that you want to transmit, and it's random, and it's identical, and it's secret. So Alice and Bob have this string, they share this secret, but nobody else does. And then what Alice is going to do, she's going to take the plain text, that is a technical lingo for the message, and add it to this binary string known as a cryptographic key, this random thing that is here in red. And this addition goes like a binary addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, but in binary 1 plus 1 is equal to 0. So that's the only thing to remember, and otherwise it's just like a regular addition. And you have a cryptogram here. Now, you can send this cryptogram via over unprotected channels. So it goes through any channel whatsoever. And even though the plain text has a statistical pattern of a natural language, the key is truly random. So when you do this addition, what you get is a completely random cryptogram. So the cryptogram, because of this addition process, acquires the randomness of the key. You don't see, if you run a statistical analysis on this thing, it's just random. You don't see any pattern whatsoever. So therefore, anyone can eavesdrop, look at this key here, look at this message, encrypted message here, this cryptogram, and nobody will be able to make any sense out of that. Except Bob, of course. This guy gets the cryptogram, he has identical key, he performs exactly the same operation and recovers the plain text. So the message is reconstructed because he adds this randomness to the random cryptogram and recovers the plain text. Now, Claude Shannon managed to show that if you use this under the following assumption, if the key is truly random, not known to anyone but Alice and Bob, as long as the message and never reused, then the system is absolutely secure. You can prove it. Basically, there's no way to break it. So in a way, end of the story, right? There you say, okay, fine, we have a perfect cipher. So why am I just going to talk for another 20 minutes or so? Well, the thing is that there's a problem with this. I wonder if you can see what the problem is. Can you? Any guess why this? Correct. So you have to use once, and then therefore. You can't establish the key at first. Right. So that's the right way. So in other words, the issue is, because the key, every single time we send a message, and mind you, Alice and Bob can be miles away from each other, right? Every time we send a message, we just waste we basically use the key. We cannot use the same key. So there is a need to generate those keys all the time. And so this is known as the key distribution problem. How Alice and Bob, we made this tacit assumption here that Alice and Bob have this key in the first place, right? But how come? Okay, they could meet secretly, write down on a piece of paper or whatever, and then just go into different locations. But if you want to really continuously communicate in a secret way, then you have to find a way to distribute those secret keys. Those keys are meaningless, there's no message there. Those are random characters, but there's value in this randomness because Alice and Bob share this random secret. And if you can do it, then it's just great. That would be great. But the question is, how are you going to do it? So suppose Alice is here in Oxford and Bob is in Warsaw, and how could you possibly do it? Sending key over any unprotected channel is foolish, of course, it's prone to eavesdropping. Is there a way to do it? And that's actually the question in crypto. And there are basically two answers to this question. One comes from a beautiful piece of mathematics that was originally proposed here in the UK by people working for GCHQ, Government Communication Headquarters, but that was not published for about 2-3 years, and the whole idea was reinvented independently in the United States, and it's known as a public key cryptosystems. And this is basically what you use on a daily basis without even realizing that you are using it. Every single time you do a purchase on internet or so, you use public key cryptosystems. And another thing is quantum crypto. So basically, there are two solutions. Public key cryptography, it's beautiful, mathematically speaking, but it's based on different kind of security, and I will just say a few words about it. It's based, in a technical language, we say it's based on computational complexity, on the difficulty of certain mathematical operations. We cannot actually prove that this system is secure, to be strictly speaking. And the second solution came from physics, and it's security based on quantum phenomena. So the key distribution problem is kind of solved, but it's solved differently by mathematicians and physicists. So let me just say this is known and it's not the topic of my talk, but just to let you know in one transparency how the public key crypto system works. So instead of doing key distribution, you can design a system where there's no need for key distribution. And the way it works is a little bit like this. Imagine a safe box, okay? And imagine that you have two keys. One key is for locking the box, so it's a locking key, and the other key is for unlocking the box. So the locking key can only lock the box, it cannot unlock it. An unlocking key can unlock it, but cannot lock it. So and what you do is, well, needless to say, this box is a sort of a mathematical system, but let's stick to this mechanical analogy, it's easier to see how it works. So suppose I want you to send encrypted messages to me. Then I distribute those boxes. In fact, there's even a procedure or instruction set how to construct those boxes, and I give you my locking key. The locking key is called the public key. It's a sequence of numbers. In fact, you can it's known to everyone. It's like a telephone number in telephone directory. You can just look it up. And you have a box, so what you can do, you can write a message, place this message in this safe box, put the lid down, and just lock the box with a locking key because everyone has my locking key. At this point, you cannot even correct the message. If you're not, if you wrote something foolish there, that's it. You have to write another message because you don't have a key to unlock this message. It's just locked, and you send it to me. And when it arrives at my location, I use my private key, which I don't share with anyone. It's always with me, and I just unlock the box and read the message. Now, you may ask this, a valid question at this point to say, well, obviously, those are not two random keys. If those are two sequences of numbers, so the public key and the private key are somehow related with each other, right? They have to be. It's not that any random choice would do. And a good question to ask is, okay, knowing how the system works and knowing the public key, is it possible to reconstruct the private key? And the answer is, yes, it is possible. However, the process of doing this to take you from the public key to the private key is, computationally speaking, extremely resource consuming, time consuming, memory consuming. It's based on certain mathematical operations which are known to be difficult. And difficulty is measured by how much time or memory or computational resources would it take if the size of the problem is increasing. So in this case, it is factoring, meaning that given a number, you have to find prime factors. So for example, if I give you a number 15, then you immediately say, okay, 3 times 5. 3 is prime, 5 is prime, and 15 therefore is decomposed into 3 times 5, so that's the factoring. But if I keep on increasing the size, if I give you a number that is not 2-digit, like 15, but 200-digit, it will be much more difficult. In fact, with every single extra digit, it will take twice as much or so. So it will be exponentially difficult for you to figure out what those prime factors are. Interesting, right? The opposite operation, multiplication, is very easy. Just increase the difficulty grows as a polynomial function, but in this case, as exponential, and it's considered very difficult. But you know, the problem is, the reason why we cannot prove that those ciphers are really difficult is because nobody knows. Maybe factoring can be solved in an efficient way. We simply don't know how to do it. It's actually worse than that. We know how to do it on quantum computers. We don't have quantum computers, but we know that if we had quantum computers, we could have done it. So in a way, you know, quantum physics as such takes away security of public key cryptosystem, because as soon as Google or Alibaba or Baidu or whoever builds a quantum computer, then those public key cryptosystems, or most public key cryptosystems, will not be secure anymore. And the one reason why people are concerned now is particularly, you know, the spooks like the National Security Agency in the US or GCHQ in these countries. They're interested now in, if you're looking for a good mathematical project to work and you have some predilection for crypto, then something that goes under the label quantum immune cryptosystem or post-quantum cryptosystem is the place to go for. So the idea is basically, okay, factoring and cryptosystems that are based on factoring are not secure anymore. So that means that some related problems based on discrete log, on elliptic curves, are also not secure. So that means, for example, that the whole security of digital signatures, that means that Bitcoin will not be secure as it is if we have quantum computers. Is there anything that we can do about it? Can we design classical public key cryptosystems that we know that are immune to quantum attacks? Even if we have quantum computers, there will be sort of a certain layer of security. So NSA has now a call. If you have any good idea, you can, you know, it's in a public domain, you can simply tell them your idea how to protect information in the quantum age. But, you know, the one way of doing this is to use quantum crypto. So you just use quantum physics. On one way, it plays a destructive roles because it kills the good existing public key cryptosystems, but on the other hand, quantum gives back in terms of perfect security that even if you have quantum computers, they will not be able to break quantum crypto devices. The problem is quantum crypto is not as flexible as universal as public key cryptosystems. So let me just then take you into this quantum domain to tell you how it works. That's maybe less important. So the story actually pretty much goes back, or I can claim that it could be Einstein who could have invented quantum cryptography. He didn't, but you know, at the time when quantum physics was the really hot topic to work on, mostly in Europe, Einstein was already well-established, very eminent physicist in Princeton, and he was a grumpy guy who didn't like quantum physics that much because Einstein didn't like the fact that you can only make statistical predictions. You cannot just say that something will happen. And he said, well, you know, this must be provisional. That cannot be really, this is not science. In science and in physics, we should be able to make predictions. And it's a little bit like, you know, statistical physics that you use maybe certain phenomenological statements. So sooner or later, quantum physics will be substituted by better, more precise, more elegant theory. So that was his view. And, you know, old grumpy Einstein came up with many ideas undermining the foundations of physics, this way or another. And, you know, Einstein, being Einstein, he was actually quite clever. It turns out, you know, some of his papers from that period of time, so this is like late Einstein, you know, he's already known for special relativity, for general relativity. At this point, he takes on quantum physics and he tries to find the underlying physics, but he cannot find anything better. So he's attacking it in all kind of ways, saying, well, you know, look guys, if you make this assumption, there's a problem here and there's a problem there. So, and then according to Einstein, there's not only a problem with the fact that you cannot make specific predictions about the outcome of some experiments, but the problem is that, you know, if you push it to the limit, there's even an issue with being able to assign what he calls element of reality to certain things. So he says, you know, certain properties cannot be even assigned numerical values. You cannot even say that they exist in some sense because you don't know what they are. And that's a bit bizarre. So that paper that he wrote with Boris Podolsky and Nathan Rosen, known as the EPR paper in the community, is actually, even though it's a negative paper because it says, you know, the quantum physics, you can see that the title is, can quantum mechanical description of physical reality be considered complete? He says, well, even though it's a question mark, Einstein makes a clear statement that, yeah, it cannot, according to him. And so let me just tell you very briefly, not in the Einstein way, that's a beautiful paper to those of you who are interested in history of science, but maybe it's easier just to explain a slightly different modern example what we mean by that and how this lack of reality can be used for cryptographic purposes. So Einstein basically, well, let's forget about Einstein for a while. Let me just take an example of polarizing photons. You know that light is, the quantum of light is a photon, and it can be polarized, and polarization is just intrinsic property of a photon. And it can be polarized along different directions, so we can say, we don't say that this is a polarization per se, right? So it's a polarization of a given direction. So once you fix direction, you can measure polarization. Like in this hypothetical device, you put your polarizing filter or whatever along a certain direction, and given that, you can have two outcomes, say +1 and -1 in some units of h bar. So polarization is, you know, in any measurements we can get those two results. So in this sense we can say, okay, well, for any given direction we have a measuring device that can measure polarization, and our classical intuition basically tells us that, okay, so obviously the whole thing, the polarization was there, the measurement reveals pre-existing value of this polarization. It's already there, and the measurement is not creating this value in any way, but it's just you know, allows you to reveal what it is before it actually entered this device. So that should be clear, right? Now, the Einstein then came up with this argument where he considered two particles, and this is again a modern version of the whole thing, where you have two photons now coming from a source, and one photon will go to Alice and another photon will go to Bob, and Alice and Bob will be making polarization, will be performing measurements of polarization along certain directions and checking whether they can see any correlations between those polarizations. So so let's see. So the question would be, you know, they want this experiment in a way will reveal to us whether, as you will see in a moment, where the photons have predetermined values of those polarizations. Yeah, that's a bit of a shift, I don't know. Just anyway, so this box supposed to be, for some reason, just it's supposed to be around Bob, but never mind. So we ask Alice, in this experiment, you have, imagine the following scenario. There is a source of those, what are called entangled photons, and the source will emit photons over and over and over again. And one photon will go to Alice, another photon will go to Bob. Alice will choose between two different types of polarization that we call here A1 and A2. So she will measure a polarization along direction A1 or A2. And Bob will measure polarization likewise around two different directions, B1 and B2. Don't worry, this is the most technical slide that I have. And now, think about A1, A2, B1, and B2 as random variables, binary random variables, because A1 can have two different values, +1 or -1. The same for A2, the same for B1, and the same for B2. So those are binary random variables. You don't know which one will happen, but you know that one of the two. And they will choose for each incoming photon, they will choose randomly, independently from each other, which one they are going to measure. So in some cases, for the first pair, Alice may measure A1 and Bob may measure B2. And then for the second one, Alice again may measure A1 and say Bob B1, and so on and so forth. So you know there are 4 possible configurations, and they will just go on and do all these measurements and make and register the values. And then we may consider another random variable that is here constructed as in this way as a sort of a linear combination of those 4 binary random variables S. So if you look at it, and you know that A1, A2, B1, B2 can only be plus or minus 1, and you look at this expression here, you say, one of these terms is 0 and the other one has to be 2 plus minus 2, obviously, because B1 and B2 are either the same or different. And by a simple visual inspection of this formula here, you can see that S can take only 2 different values, either plus 2 or minus 2. And therefore, if you take the average, if you run this experiment, you can evaluate the average value of S, and this average value will be somewhere in between minus 2 and 2. And if you follow this argument, congratulations, you know what is known as the Bell inequalities in physics. So this is like one transparency explaining what is known as the Bell theorem or CHSH inequality or Bell inequality. So this is a very simple statement about correlation, saying that if A1, A2, B1, B2 do have numerical values, then this statement here has to be true. So this is the Bell inequality. The average value of S has to be somewhere between minus 2 and 2. Very simple. Mathematics is just trivial, right? Any person can follow this after elementary school pretty much. But physical interpretation is not trivial. Because you may say, okay, well, so obviously this will happen. You run this experiment, this has to happen. How it could be otherwise? Those polarization does exist, that there is a numerical value. Well, here we come. There was a chap by the name of John Bell who translated this idea into experimental proposition, and it was experiments were performed. And at the very beginning, I have to say, it was almost like a drama. In sort of the first experiments performed somewhere at Berkeley showed that, okay, Bell inequalities are probably violated. And it was using the old-fashioned technology of entangled atoms. Then on the East Coast, in Harvard, the Bell inequalities were not violated. They did another experiment in Texas. And Texas was, not sure. And then probably the most spectacular and decisive experiment was performed by Alain Aspect in France, in Institut d'Optique in Orsay in 1982. So there it was beyond doubt, and Alain put so much effort and came up with a beautiful experiment. At this point, most physicists were actually persuaded that the Bell inequalities are violated. In fact, quantum mechanics says that quantum mechanical prediction says that actually this average value should be somewhere between 2 square root of 2 and minus 2 square root of 2 and 2 square root of 2. So it can go outside this minus 2 and 2 interval. And that really what was observed. And since then, many beautiful experiments were done. Actually, a couple of years ago, the most convincing one was probably performed in Holland. And most physicists now pretty much, I don't think, there are a few crackpots who of course believe that, there are hidden variables, but most of, we truly believe that this is the case. But if this is the case, so what are the consequences? What it has to do with the scenario I was describing? Well, actually, the line of argument is, if it is indeed the case that we cannot associate numerical values to the polarization prior to those measurements, so that means that those values didn't somehow exist. They didn't have physical existence. This element of physical reality that Einstein referred to was not there. And if it was there, though, those values were not available to anyone, including eavesdropper. It's only when Alice and Bob measured them, only then they became sort of a physical element of physical reality. It's weird, you know. Okay, if you don't find it surprising, think again. If you find it surprising, you are in good company. You know, just most people find it surprising, and it's actually shocking. It's amazing. You know, one of the most profound discoveries in physics, which really questions our understanding of reality, is actually very simple. Mathematically speaking, it's actually very, very simple. It's just the physical interpretation of it is a mind-boggling. So then, you know, I was, you know, when I was doing my PhD here, I was a little bit taken by it in a way that I thought, you know, it's weird, and you know, maybe because of some interest in crypto, I said, well, of course, you know, if this is the case, then you can, the same test that you use for checking whether those values do exist or not, that can be used for testing for eavesdropping, because if eavesdropper was there, those values will be there. The guy, whoever eavesdrops, would have substantial knowledge about it, and therefore you wouldn't see any violation of the Bell inequalities. So then you can turn the testing for the violation of Bell inequalities was equivalent pretty much to testing for eavesdropping. And you know, it was, at the time, was a wacky idea. I didn't think anyone would take it seriously, but people did. And I persuaded John Rarity, from a colleague of mine who works what used to be called Defense Research Agency. It's not far away from here in Malvern. And then after a while it became known as DERA, the Defense Evaluation Research Agency, and then was privatized. It's now called Kinetic. And so John John Rarity and Paul Tapster and I decided to make a proof of principle. But John, you know, the funny thing was that even though we wanted to set up this experiment and run it, the local management was not very happy about it for all kinds of reasons. First of all, those of you who are not from United Kingdom may not know that in this country, institutions that do crypto, government agencies that do crypto, are sponsored by Foreign Office most traditionally, and Defense Research Agency was under Ministry of Defense. So Ministry of Defense is not supposed to fund any work in cryptography, and the bureaucrats said, no, you cannot do this, you have to talk to someone else. And in any case, according to John, you know, the perception was that if he's not taking his laser and he's not aiming at a tank, he's not doing any research as far as the Defense Research Agency was concerned. Not talking about, you know, try imagine to explaining Bell inequalities to those guys, you know. Anyway, at the end of the day, it was just with all kind of anecdotes and so on, we managed to set up this experiment and demonstrate that it works. It was classified for a while, but it became declassified, and so it was even later on publicized in Scientific American. And, you know, since then, my interest in the field somehow was sort of, maybe I was less into this because it became too practical to my taste. It's just, and today it's just everywhere, you know, not necessarily the system that I propose, but also the systems that two colleagues of mine, Gilles Brassard and Charlie Bennett, proposed slightly different, and they did it independently. But there are beautiful experiments all over the world, from Switzerland to Tokyo to Seoul, and even, you know, beautiful experiments performed by Chinese, where they are now having a system which allows them to send entangled photons from a satellite, which carries the name of a Chinese philosopher, Nicias, to ground station in China. So it's by far probably the most spectacular thing when it comes to the key distribution. And this is hitting the headlines, so it was very difficult not to read about it. So, you know, altogether, just to conclude, I can go on and talk about those wacky stuff, but probably there's not enough time for that. There's a long path from Skittily, substitution ciphers, Enigma, public key cryptosystem that we know may not be secure in the quantum age, to quantum crypto. And quantum crypto offers more surprising. The more you go into the system, you realize that there are many beautiful things about it. For example, if you do the key distribution from a satellite, that you don't even have to protect the satellite. An enemy can control the satellites because the two users on the ground, Alice and Bob, can easily check if they see the violation of the Bell inequalities. They don't care where those photons come from. They could be even just provided by your adversary. That can also be true about the devices they use, and so on and so forth. So there's lots of beautiful science about it. And if you're interested, so this is a semi-technical paper that I wrote with a colleague of mine, Renato Renne, where we try to go to the limit and see, even if individuals are manipulated a little bit or they don't have a trusty devices in the lab, can they still establish secret things? So those of you who feel like learning a little bit more about it, I encourage you to just read about it. So let me just conclude the whole thing with a little puzzle. I will give you the answer to this puzzle, but a question, interesting question that is asked in the context of cryptography or quantum computing today is, why something that seems to be the provenance of mathematicians or computer scientists, why is it the case that physicists who entered this field and somehow made substantial contributions to it? How come physicists managed to achieve certain things and find solutions that computer scientists couldn't? And I think the main answer to this is that physicists took any information processing as a physical process, be it computing or key distribution. It's considered as something physical. Information is encoded in physical objects. It doesn't exist in abstract terms, right? We can think about it that way, but any real information processing is done by physical devices. Your computer, your laptop is just something that has to follow the laws of physics. So here is a puzzle that I like to give sometimes when we interview people students who come to Oxford for the entrance exams. So those interviews in colleges where we want to give them some questions to see how they think. Not so much how much they know, but how they think about certain problems. So this one I like because it tells you whether you think more as a mathematician or more as a physicist. So if I give you this, I specify this puzzle in a moment, but if you find it difficult, that means you are probably a mathematician or a logician or someone who thinks in very abstract terms. But if you find it easy to solve, then most likely you are a physicist or an engineer or some practically minded person. The puzzle is like this. So there's this guy in front of two rooms. In the first room on your right are the three switches that you can see in position off. And in the room on the left are old-fashioned light bulbs. And we know that there's one-to-one correspondence between the switches and the light bulbs, but you don't know what it is. Now your task is to figure this out, and the rules of the game are this, that you can go into any room, but only once. Once you leave the room, you cannot enter the same room. And under this condition, of course, once you are in a room, you can do whatever you want, but once you leave, that's it. You cannot go and check what you did there. So under those conditions, can you establish or figure out what is this one-to-one connection or correspondence between the switches and the light bulbs? And if you're a mathematician, you say, no, it's not possible. And you say, well, you can come up with all kinds of arguments why it's not possible, but one would be, well, if I go to the first room, it only makes sense to go to the room on the right with the switches. And if I put one switch in position on, I leave the room, I go to this room, okay, one light bulb is on, but there's ambiguity about the other two, right? Or, you can consider all possible scenarios. For example, if I put two switches in position on, then there will be ambiguity about the two light bulbs that are on. So no matter what I do in the first room, for all possible combinations, there will be always ambiguity. And you can say QED, I can prove that it's impossible. Okay, give this puzzle to an engineer and say, easy. It's very easy. All you do is, of course, you go to the room with the first room on the right. You put the first switch in position on. Well, take the second switch, put it in position on, say, for 10 minutes, switch it off. Then you go to the other room, one light bulb is on, one is still warm because it dissipates heat, and the other one is off. So this way, you know, it only works with old-fashioned light bulbs, right? So this with but you know, what happened here is if you think about this as an abstract thing, then you see there's no solution to it. But if you then realize it's real, it's for real, it's physical, then you find a solution. So it is the same with discovery of quantum physics. And if you take computation or information distribution or key distribution as a real physical process, then you have this extra handle, like the heat dissipation here, which allows you to solve certain problems which were not considered to be solvable, or at least you can solve them more efficiently. And hence, this is actually a good illustration that you know, you have to think information in physical terms. You have to, and if you think about information in physical terms, then you have probably more insights. It doesn't, of course, work all the way. Sometimes the power of abstraction is very important, and for some other problems, you're better off thinking in abstract terms. So I'm not saying that this is a panacea for all problems in information science, but nonetheless, it's certainly something that should be taken into account. And in many ways, if you think about computer science, modern computer science, one can make a claim that agitates all computer scientists that they are actually experimental physicists or theoretical physicists, because they construct devices and they describe devices that are, after all, physical devices. And all this computation is just like a huge physical experiment where you prepare input and you check the output. And what happens in between is an interesting physical process to which you give some logical meaning, but nonetheless, it's a piece of physics. Anyway, so I just should add that, you know, there are lots of interesting stuff going on, and if you still at this part of your career where you think what to do next, consider quantum information science as a good topic to enter. Thank you very much.